Hello students. My name is Shayan Mitra. I'm the faculty member of Department of Electronics and Communication Engineering of the College of Engineering and Management. Today, as we have discussed earlier in the previous lectures, we have described what is the LTI system, the power system is, and we have described what is LSI system is, and we also described why what is an impulse response, what is the impulse signal, and how a signal can be formed or represent using a addition of impulse signal. As a specific signal can be realized using a train of signal that could be added up and provide us with a specific signals, specific discrete time signals, and so on. We let's this is the lecture number 8, and code name is EC303. Now in today's lecture we are going to discuss what is the convolution processing and how it works, what is the specific significance and importance of a convolution. Okay, so after completion of this lecture, people will easily understand what is a convolution means and why it is important, why it is required, and what is the significance of a convolution in case of an LTI-C system, okay, or LTI system, linear time invariant system. Okay, so let's begin with the lecture. Okay, so as I have discussed in an earlier lecture, that how discrete time signal can be written as the summation of the combination of linear signals. So now, as you've realized that the next step that we are going to include here is the basic function, that what is the significance or the importance of writing a specific signal, specific discrete time signal using impulse signals, or the combination of impulse signals. Okay, so now suppose that in this it is also that so in this segment that we realize that we can write this del of n minus k, the impulse signal. Now this is the shifted unit impulse signal. Now suppose we have fed this shifted unit impulse signal to a linear system. First we are taking a signal where the signal is time varying. Okay, suppose the time varying signal. So when you are using a time varying signal, what we will get a when you fed impulse signal, we will get a response, the specific signal. When we fed it through a linear time varying system, we will get a response such as this. Okay. So from that we can realize that the response of yn of the linear system to the input x of n in equation 2.2, that we have already realized that is simply the weighted linear combination of this basic response. Now the basic response are nothing but the x of minus 1 and the impulse signal. Okay, so that is with the input x of n to a linear system expressed in the form of equation 2.2, the output of y1 can be expressed as this. Okay. So now this expression can be also written in a subscript form, where we'll use it. The signal x of n is applied as the input to a linear system whose responses are this: h of minus 1 and h of 0 and h of 1 n, or this, and to the signals of this. So when we are when you fed all these impulse signals to a specific digital system, we will get a response such as this respectively. For del of n minus n plus 1, we will get a response such as h of minus 1 of n. For del of n, we will get a h of 0 of n. And for del of n minus 1, we will get a response such as h of 1 of n. So these are the response that we will get. Now suppose, if we have to use it as a general form, so when we are providing it with a linear time varying system, we will get this kind of responses. So this is the x of n, this is the response of impulse signals when we when we fed all those impulse signals to different digital system, we will get this kind of responses such as h of -1 and h of 0 and h of 0, h of 1. So when we add them, we will get a specific response. Okay. Now suppose in place of, instead of using a linear time varying system, we have taken a linear time invariant system. Now in case of linear time invariant system, what we will get? We will get the responses for the impulse signals which are very much alike to the responses of the system as it is undelayed. It means we will not use the word undelayed, we will use the word preserved. When we are using a linear time invariant system, we will get the response for the impulse signals which are mainly not in a distorted form. Okay. So suppose these are the responses of an impulse signal for linear time varying or linear shift varying system. Okay. Now if we considering here as the linear time invariant, where the waveform will be preserved, we can write the signal in the form of this, because in case of linear time invariant system, the responses to the impulse signals will be very much alike to the responses. It means it is alike. It means when you are provided with the impulse signal, the response of the impulse signal for a linear time invariant system, which can be written as h of k or h of n. Okay, those are very much alike to the impulse signal which are being fed to the digital system. So the input that has been fed to the impulse digital system and the output that has been extracted for that input, for that impulse signal, or it could be read as or spelled as an impulse response, that are very much alike. Now suppose that we have in the earlier lecture what we have realized that y of n can be written as summation of k of minus infinity to plus infinity of x of k into del of n minus k. Now as we are using a linear time invariant system, as we know that in case of linear time invariant system, when you are fed impulse signal to the digital system, we will get the response, the impulse response, and that impulse response are very much alike to the input signal, which is the impulse signal. Okay. So the impulse signal that has been fed to the system and the impulse response that has been extracted from the digital system, which both are very much alike. So that specific equation where we have write that y of n is equal to k of summation of k of minus infinity to plus infinity of x of k into h of del of n minus k, it could be written as x of k into h of n minus k, where summation is k of minus infinity to plus infinity. Okay. And this particular generalized equation can be written as y of n. Okay, y of n into y of n is equal to x of n into h of n. This is the formula. Can be written as, and also it has been known as the convolution sum or superposition sum, because it is also known as superposition sum because without the linear system, without a linear time varying system, we cannot establish this relation. Without being a linear time invariant system, we cannot have this kind of proposition or this kind of proof, which is mathematically and practically feasible. So that's why it is known as convolution sum or superposition sum, and the operation on the right hand side of equation 2.6, this is known as the convolution of the sequence. So this is the convolution of the sequence x of n. Okay, so the whole sequence x of n can be written in this format. Okay, and the same way this is the h of n. Okay, so any kind of so this is the convolution of a sequence of x of x and x of n and h of n. And what is the h of n? H of n is nothing but the impulse response of the impulse signal which has been fed to the digital system, which is considered as the linear time invariant system. Okay, and symbolically it could be write as this way. Okay, so this is nothing but the convolution. Now next step of after understanding what is convolution sum is, we are going to give one or two examples, and we will realize why it is important to what is the significance of convolution, why we have introduced the convolution sum or superposition sum. Okay, so let's begin with it. Now this is the first graphical representation of convolution sum. Suppose this is the x of n, this is the input, and we have provided this is the impulse response first. This is the second impulse response of x of 0 del of n. Okay, these are the subscript that we have used. All these outputs of these inputs are different from each other. Now after we add all these signals, this is the signals. This is the x of n that has been written here. Three different signals. One, nothing is not very much. The x of n, this is a signal that has been written here in three different. It's nothing. We just decompose the whole x of n, this x of n signal, this discrete time signal, in three different parts. We can write this signal. We can decompose this x of n in three different parts, okay. And then we will convert this x of n, x of minus 1 into del of n plus 1 to this x of minus 1 into h of minus 1 n, h of 0 n, and h of 1 n. Okay, nothing but with the impulse responses. We will fed to this, we will get this result. We will fed this to get this result, and we will fed this and we will get this result. And after adding all these three, we will get the y of n. So this is the input and this is the output. So this is another way. We can fed this directly, okay, and we'll get this result. Or we can fed this x of n in the form of these three different signals. We will get three different output. After adding all these three signals, we will get the same specific results. So this is basically another way of saying that you are using a linear time invariant system. Now if this system is not a linear system, we are not going to get this kind of result. Okay, so first of all, we just decompose these three signals. We decompose this x of n in three different signals. We'll get the output individually of each and every signals. Then we add all these up and we'll get this output signal y of n. Now just because it's a linear system and also time invariant system, we'll get this result. Okay, or we can provide us, we can achieve this kind of a result. So this is the first realization. Now this specific functionalities of a linear time invariant system will be useful when we are going to create or design different kind of digital signal process or digital signal machines. It will be useful for this specific reason, as because it's a linear time and invariant causal signal. Causal, we could put aside the causal part for the next lectures. In this picture, what we have realized here, that one specific signal can be decomposed in 3-4 different signals. Then we'll fed them to different same specific digital signal. After getting the output, we'll add them up and we'll get the desired output. Okay, so this is the first one. Now we are going to understand how the convolution works, how the convolution goes along. So this is the first example. We can take this example. It's a very much fairly easy example we are going to discuss here. We're going to understand how the convolution works. First step of this example is that simple. We are considering LTI system. As I already said, we will only consider LTI system right now. Okay, for this specific convolution. Okay, so consider an LTI system with impulse response h of n and input x of n, and this has been illustrated here. So for this case, so this is the h of n. Okay, this is the x of n. So this is the input signal. This is the impulse response of that specific digital system. Okay, which are 0, 1 and 2. Okay, because we have taken the sample points of 0, 1 and 2. Fine. So this y of n can be written as x of h, where h of n minus 0. Now as we are shifting through the points, we have to put k is equal to n, so n is equal to 0, we will get a value 0.5. For x of 1 we also get a value h of n minus 1. Now as we put k is equal to n is equal to 1, so we will get h of 0, which is 1. So value of x on 1 will be 1. Okay, and for value 2 we will get h of n minus 2 and x of 2. But as we have already know that at x of 2 the x of n value will be is not present, so we will get only these three values. Okay, so we can write this in a matter of format that this is all the one value. So this is at 0 we will get 0.5, at x of 1 we will get 2 of h of n minus 1. Okay, so the first, now so this is the output. Okay, 0.5 h of n and plus 2 into h of n minus 1, because as you can understand the x of 2 is not, it can't be realized. So when you put x of 2 it will be 0, so we will not get any signal. So y of n can be written as this. So now the next step is now what you have realized, this is the x of n, this is the h of n. H of n is the impulse response. This is the input signal that is going to be fed into the digital system. So what we have done, we have taken according to the general concept of summation of k is equal to minus into the plus infinity into is of x of k into h of n minus k. So we will put the value of k for 0, we will get this. For k of 1 we get this, and k of 2 we will get 0, so it has not been written here. Okay, so now we'll play with this two specific parameters. So what we will get here, first 0.5 hn. Now 0.5 hn, now 0.5 into hn. Now the value of hn is this is the hn, is the impulse response. Okay, so when you multiply it with 0.5 we will get this is the result we get when we multiply h of n into 0.5. Okay, the next step, we will multiply it with 2 for h of n minus 1. Now this is the h of n, so h of n minus 1 will be a delayed signal. Okay, yes, this will be a delayed signal. So okay, so as we have multiplied with the 2 we will get this. As we multiplied with h of n into 2 we will get this. As we know that h of n, now we are taking it as a h of n minus 1, so the signal will be delayed, as we have delayed the signal with h of n minus 1, so we will get the specific signal. As we have multiplied with it with 2 we will get, so when we multiply with h of n minus 1 into 2 we will get this specific signal. Okay, this is the other signal that you have realized. Okay, so now if we just add up all these signals, we add up this is 0.5 into 2. Okay, this 0.5, this 2.5, this is also 2.5. So this is the y of n. So and that is the way we will realize the convolution of a specific signal. Okay, so now if we just go through it again. So first step of convolution is, we will take the general form of y of n. The y of n can be written as the summation of k of minus infinity to plus infinity of x of k into n, h of n minus k. Now when we put the value of k here, it will be 0. Okay, we will get a value. For k of 1 we will get a value again, and that is 2. So we will put all those values. K is equal to 0, put k is equal to 0, put k is equal to 1. What we get? you get 0.5 h of n plus 2 of h of n minus 1. Okay, and also what you have realized here, that this is the impulse response. Okay, you already know this is the impulse response of what? This is the impulse response of that specific system, specific digital system. Now it is also important to understand that depending upon the system, maybe the system is linear time invariant, the impulse response of different system will be different. For different, suppose we have fed with two different digital system with del of 1 and del of 1, so the impulse response is not important, it is not accurately the same. Okay, so it depends upon it. So the sequence of these are the two echoes of the impulse response needed for the superposition involved in generating y of n. Okay, so these echoes are displayed in figure 2.3b. okay, so this could be written as, now as you can realize that 0.5 into h of n, we will get this result, and when we multiply 2 to h of n minus 1, we realize this. Okay, yes. Okay, so this is the value, and after adding all this up, we will get the value y of n. Okay, so this is the way of doing a convolution. Okay, the first step, so first step will be, we will multiply this, we will put the value of x of 0, n of 0, n of 1, sorry, k of 0, k of 1, k of 2, and according to it we will get the convolution generalized equation, and we multiply it with the impulse response, as you have already got this impulse responses, and then we add them up. Okay, after adding all them, after adding 0.5 plus these two, we will get this y of n. Okay, so this is the first example. Okay, now if we take another example here, what we will get here? Okay, suppose suppose this is h of k. Okay, this is h of k. Now this is h of n minus k. Okay, so where n is equal to 0, n in case of n is equal to 0, we get n of minus 2, n of minus 1, n of n, and when h of 0 minus k, we will get minus 2, minus 1 and 0. For h of 1 minus k, we will get this, h of 2 minus k, we will get this, h of 3 minus k, we will get this. Okay, so after using this, we will get this result. Okay, so this is the way of doing any convolution. According to that, we will realize it. Okay, so the same way we can also realize other values. Suppose this is a signal that could be written as x of k into h of n minus k, which is written as alpha k, alpha to the power k, which is the value of k should be in between 0 to n. So the x of n of alpha alpha to the power n un is realized in this way. Okay, so and also the impulse response or the step response of this specific system where we have to feed this signal is this. Okay, this is the signal x of n and h of n is equal to. Now we know that for n of greater than equal to 0, the y of n is equal to summation of 0 to n alpha to the power k. So using the result of problem 1.5, you can write this. You can write this. Yes, you can write this function. Okay, so then you have realized here that how the convolution will take place. Okay, so another thing that is an important factor that we should understand here, that in case of the first example, that we have realized here, that in case of h of n minus 1, what has happened here? It is not been delayed here. We have to realize that when the value, this is the value of k, this is the value of 1 is the k. Okay, so as from the shifting property of the generalized form of convolution sum, what you have realized, that until and unless the value of k is equal to n, the whole value will be 0, right? So for h of n minus 1, the value of n have to be 1. Okay, without that we can't get the we can't realize the form. Okay, for that reason, that this is the impulse response for h of n. So for h of n minus 1 it will be started from here. But in case of when we are delaying or advancing a function, now suppose we have used a normal discrete time signal where we have to delay the function. What will do? Delay the signal. We have to just minus 1 or plus 1 the function. By minus 1, by using minus 1 we can delay the advance the function. Okay, it will be start from minus 1. That value will be start from minus 1. But in case of h of n minus 1, where this is the we have to understand that value of n is k is equal to n. Without the k is equal to n, the impulse response will be 0. So that's why this signal has been started from here. The impulse response has been started as we have used h of n minus 1. The signal will be has been started from here. Okay. So we'll end this lecture here, and this next lecture we'll continue with some different examples of convolution, and we'll understand how the step response work and the basic system properties work. Okay. Thank you.